Welcome to another edition of Math for No Reason. In this edition, we are looking at an interesting problem. So let us first look at the definition of Kn, which is the complete graph on n vertices. That means if we are looking at say these four vertices, which we call A, B, C, and D, then there is an edge between any two of these vertices. So this graph is called K4. The triangle is an example of a graph, a complete graph on three vertices, and this is called K3. Similarly, if we have say five vertices and we connect each of them with an edge, then this graph is K5, the complete graph on 5 vertices. And similarly, for if you have n vertices, then a complete graph on n vertices will have NC2 edges, an edge connecting any two of these vertices. Now let us look at the definition of what is known as the Ramsey number. Now the Ramsey number, which we denote as R small k small l, is the smallest integer n such that in any two coloring of the edges of Kn, the complete graph on n vertices, by the two colors, red or blue, and whenever we do this, either there will be a complete subgraph of k vertices, all of whose edges are colored k, that is the subgraph will be k small k, or there is a complete subgraph of L vertices, all of whose edges are blue, that is the subgraph is k subscript L. So RKL is the smallest integer having this property. Now we have to prove that if NCK 2 to the power 1 minus KC2 is less than 1, then RKK is greater than n. So let us first answer the question that in how many ways can we choose k vertices out of n in Kn? The answer is simple. We can choose k vertices out of n in NCK ways. So there are NCK choices. So let us list all these NCK choices as choice 1, choice 2, choice NCK. So these are the NCK choices that we have. So consider the choice Ci of k vertices out of n, and we consider the subgraph, and this subgraph is complete because Kn is complete. So this subgraph is also complete. Now what is the chance that this subgraph with k vertices is monochromatic? So AI is the event that the complete subgraph associated with choice Ci is monochromatic. So we randomly color the edges. So the probability of an edge being red is equal to probability an edge being blue, and that is equal to 0.5 or just half. Now we try to compute the probability of the event AI. Now since this is a simple exercise in classical probability, all outcomes being equally likely because of the random coloring process that we are using, therefore the total number of ways in which this coloring can be done is 2 to the power kc2. There are kc2 edges in this complete subgraph. Each edge can be colored either red or blue. So therefore the total number of ways the edges can be colored red or blue is 2 to the power kc2. And out of this, in how many ways we can color this complete subgraph in a monochromatic manner? That means all the edges are either red or blue, and that can be done in only two ways. So the probability of AI is 2 to the power 1 minus kc. So the probability that the complete subgraph associated with choice Ci is monochromatic is 2 to the power 1 minus Kc. And there are NCK such choices. So since there are NCK choices, we are looking at the probability of having at least one complete monochromatic subgraph, and that is the probability of this event A1 union A2 union A NCK. Now that is less than equal to, by Boole's inequality, summation of I is equal to 1 to NCK probability of, and probability of AI does not depend on I, so this is nothing but NCK 2 to the power 1 minus. So that is the probability of having at least one monochromatic sum. Now observe that we are given that NCK 2 to the power 1 minus KC2 is less than 1, which means that the probability that A1 union A2 union A NCK complement is actually greater than 0. So this complement is 1 minus NCK 2 to the power 1 minus Kc2, and we are already given that NCK 2 to the power 1 minus Kc2 is less than 1. So therefore this is the probability of not having a monochromatic subgraph by this process is found to be greater than 0. Now recall that RKK is an assertion of a sure existence of a monochromatic subgraph with k vertices in a complete graph with n vertices. So therefore, if this condition holds, there is a probability that we can have a graph whose we can have a complete subgraph with n vertices which does not contain a monochromatic subgraph, which means that RKK has to be greater than n. So if RKK is n, we would be certain that the complete graph with n vertices would have a monochromatic subgraph with k vertices. That would have mean the probability of this quantity would have been 0. But that is not the case. The probability is turning out to be greater than 0. So therefore, we can conclude that the Ramsey number RKK is actually greater than. Thank you.